Good morning. In this video we are going to discuss about lattice structures. So, okay, here up to now we have seen different structures in IIR system and also different structures in the FIR system. So now coming to the lattice structures in both systems, IIR systems and FIR systems, how we will realize, right? So see here, lattice structures. So here firstly for FIR systems. So lattice structures for FIR systems. FIR means finite impulse response. These lattice structures are also called as lattice filter. These are also called as lattice filter or lattice realization. When compared with the other realization structures, it looks like a something different one. So here understanding also difficult when compared with the others. So we should concentrate on this and then we should practice more and more. Okay, then only we can understand this one, right? So here lattice structure is also called as lattice filter or lattice realization, and this is extensively used in this type of structures used in digital speech processing, digital speech processing, and in the implementation of adaptive filters, and in the implementation of adaptive filters. That means if you want to predict the next coefficients, future coefficients like that, so in such a case also we can use this type of lattice structures. So in digital speech processing and to implement adaptive filters, so this type of lattice structures are specially used. Okay, now coming to the here structure realization. So now see here, FIR filter, finite impulse response filter. Consider one filter with which has certain system function that is in the form of, so just consider like this, HM of Z, that is equal to AM of Z. AM of Z. Here M 0, 1, 2 and so on M minus 1. Consider like this. So now here what is AM of Z means, here AM of Z is nothing but 1 plus summation alpha M of K Z power minus K. K here 0 to 1 to M. Here M greater than or equal to 1. Okay, that means A0 of Z or AM of Z at M0 means always 1. So now consider like this. So that means FIR filter means a finite impulse response, means of course you know that H of Z is in the form, usual form is nothing but I am writing here, what is that, summation h of n z power minus n, where n 0 to n minus 1. So just simply write in general form. Okay, so we just write like this. So okay, here we just use here different symbols. So this one is equal to, almost equal to this one. See here, just I am using here k variable instead of n variable. Okay, that means here n changed into z, but here k will be changed into z. That's it only. Now here capital N minus 1 is the upper limit. Here I am taking small m. So here small m is nothing but 0, 1, 2 and so on, m minus 1. Here m and n. Okay, right? So like that, instead of n minus 1 I am using m minus 1. So m minus 1 means here, so I am writing here small m only. Okay, right, that is the difference. And then here I am separating the n is equal to 0, what is that term here. If I apply n is 0 here, h of 0 into z power 0 means h of 0 only, h of 0 plus summation n 1 to n minus 1 h of n z power minus n. In this way also we can write this equation. That means here at n is equal to 0, the term is h of 0, that h of 0 is here 1. So I am assuming here h of 0 is nothing but 1 here. So that's why here I am separating this one. So here h of 0 plus summation n 0 to n minus 1, n 1 to n minus 1 h of n z power minus n is there, right, is there. But here I am writing like this. What is that? H of 0 is 1 plus summation, instead of n I am using k, k1 to capital N minus 1 is nothing but here capital M minus 1, that is here I am taking m, right. So alpha m of k, instead of h of n I am using the coefficient symbol here, alpha m of k into z power minus k. Now m greater than or equal to 1. So now here for m0, what is that? a0 of z is equal to 1. For m0 here the value is a0 of z is equal to 1. So this is the 1 here. So m greater than or equal to 1 only. Okay, right? Here if k0, some h of 0 or alpha m of 0 is there, that is equal to 1 here. Okay, so here am of z, okay, but actually am of z means m from 0 to m minus 1, but this equation is only for m greater than or equal to 1. But what about m0 here? So that means if m0, okay, so just take the m of z as 1 here. Okay, right, that means h of z is equal to 1 for m0. So in such a way, right, that's why here equation looks like this. So don't confuse, and then just be practice, and then you can easily understand this one. Okay, now coming to the here for unit sample sequence, unit impulse or unit sample sequence, sorry, what is that, response, unit impulse or unit sample response. Unit sample response or unit impulse response of the mth filter. That means here m means filter order. Okay, mth filter is, so okay, it is represented as hm of k. So here the system function is hm of z. So here m is the order of the filter. Okay, so if I take the second order filter, consider h2 of z like that. So now here HM of k, mth order filter. So that is nothing but actually, so observe here, what is this here? HM of z. What is this? That mth order filter system function. What is that system impulse response? HM of k. HM of k. That means Z transform of HM of k is nothing but HM of Z. Z transform of HM of k is nothing but HM of Z. So from this information, so whatever we consider the filter, what is that how this system is described like that. So for that system, what is the impulse response, right? That is HM of k. That is nothing but here that HM of k is equal to 1 for k is equal to 0. Okay, so at k is equal to 0, that is equal to 1. Okay, so here already we took definition. Here this is the h of n. What is the h of n is equal to 0, h of 0. H of 0 means here what is that? 1. That's why here we consider like that k 0, hm of k is equal to 0. So such that only we have written like this one here. Okay, now coming to the next one. What is that? hm of k is equal to alpha m of k when k 1, 2 and so on m. Am I correct? So this hm of k is, right, is nothing but what is that? This one. So observe the resemblance here. This is nothing but hm of k, right? So here hm of k from k greater than or equal to 1, that means 1, 2 and so on m. So here that is nothing but the impulse response, okay, or sample unit sample response. Okay, now am of z means what is that? hm of z. Here m represents what is that? M degree of the polynomial, degree of the polynomial in hm of z or am of z. That one also represents order of the filter, order of the filter system or filter order. Okay, now coming to the next point. Okay, right, the next point is here, the here system is, what is the system? Am of z or hm of z, mth order filter. What is the input here? X of n. What will be the output? Y of n. Okay, so in such a case, how can you write this y of n? Y of n is equal to convolution between these two. So now what is that? X of n convolved with hm of n. Am I correct? hm of n. So now I am using here this one, hm of n convolved with x of n, both are equal. So now I am using the formula. What is that formula? Here k 0 to n minus 1. N minus 1 means here m. Here h m of k into x of n minus k. hm of k into x of n minus k. Now hm of k into x of n minus k means, here if you may take x of k into hm of n minus k, but for simplicity, what is that, simple calculations I am taking here like this. Okay, both of these equations are equal. what is that from the commutative law. So now hm of k into x of n minus k. So now here from this, what is that? Y of n is equal to summation k0 to m hm of k x of n minus k is equal to, I am what is that, expanding this one. That means just I am taking the 0th term separately. What is that? hm of 0 into x of n plus summation k1 to m hm of k x of n minus k, x of n minus k. Okay, so here what is the hm of 0 here? Already you have taken. What is that? hm of k at k0 is 1, and other than these values, that means other than 0, for these values it is equal to alpha m of k. I am substituting this one here. Okay, right? So here we know that hm of 0 is 1 plus k1 to m, hm of k is alpha m of k x of n minus k. So now what is the y of n? X of n plus summation k1 to m alpha m of k into x of n minus k. Okay, right? So this is the equation. So now here, so just recall the points here. So what is the first point here? It is also called as lattice filter or lattice realization. What is the second point? It is used in digital speech processing and in the implementation of adaptive filters. Now what is the third point here? We are considering one FIR filter with the system function which matches this actual system function. So here we are using h of z instead of h of z, hm of z, where m is the order of the filter. Now hm of z, that is equal to am of z. Here m is 0 to m minus 1. So that means here where this am of z is nothing but, so here we just rewritten like this. Okay, right? So from this general form we just write in the different form, that is separating the 0th term and then like a 1 plus summation alpha m of k z power minus k m greater than or equal to 1 under some assumption. So what is that here? A naught of z is equal to 1 or h of 0 is equal to 1, like that. H of 0 is equal to 1 and then h0 of z also 1. So that means m 0th order filter, what is that, system function is equal to 1. If m greater than or equal to 1, like first order, second order and mth order filter only, this system function is having this formula like that. Okay, so under these assumptions, right, 0th order system function is 1 and then h of 0 also 1, like that. Okay, then so here from this from the hm of z or am of z, now unit sample response is nothing but hm of k is equal to 1 here and hm of k is equal to alpha m of k here. That means k 0 1, so 1 to m, so this is the alpha m of k. Is just here place these what is that values from this definition only, from this consideration only, right? So that's it. Okay, now after completing hm of z, immediately complete the hm of k, then consider that system here. So it has input x of n and output y of n. Now what is the output here? So here that is the convolution between the input and the system. Now here input is x of n, so system is hm of n. Now I am taking the formula summation k 0 to m hm of k x of n minus k, right? So now here what is the hm of k here? hm of 0, we know that hm of 0 value, and hm of k, for k not equal to 0, that means k1 to m. So now in such a way, so you just separate the here this summation like this. So then you can get what is that, x of n plus summation alpha m of k into x of n minus k, right? So here up to now we have seen different steps, very simple steps. Remember, first consider the filter, that is hm of z, and then find the hm of k, and then find the system output y of n. Okay, then y of n with respect to the input and past inputs. Okay, now from this here we have to realize the what is that, lattice structure. Lattice structure. Before going to lattice structure, how can you realize this one? By using direct form. So we will see now. Okay, right? So and then only you can observe what is the difference between direct form and lattice form. So first, how can we develop this one? By using the direct form. Okay, so usual form already discussed in the FIR realization structure, first type. What is the direct form structure? So now here see this direct form structure. Direct form structure of the FIR filter, which is represented in the previous case. Okay, right, that is nothing but what is that, y of n is equal to x of n plus summation k1 to m alpha m of k, then x of n minus k. Now here for understanding, so I am writing this one with respect to z variable, that means by applying the z transform on both sides, and then expanding this one also. So alpha m of 1, x of n minus 1 means z power minus 1 x of z plus alpha m of 2 z power minus 2 x of z, and so on. Alpha m of m z power minus m x of n minus m x of, I'm sorry, is that x of z only. X of n minus m z transform is z power minus m x of z, x of z. Okay, right now. So here direct form means you know that, so very simple one. That means numerator polynomials are there. There are no denominator polynomials. So just it is nothing but what is that, y of z by x of z means here only numerator polynomial. That means it is nothing but a all zero system. What is that? All zero system. So now see here, you know this already did in FIR filter realization structures. So for compact form, here we are writing this one in the horizontal form, but in the case of IIR, all pole and all zero system, it is in vertical form. If you have any doubt in this, just kindly see the video related to the FIR system realization. So first draw the delay units, and then draw the multipliers, and then draw the adders like this. Okay, this is Z inverse, Z inverse, Z inverse. How many unit delays here? M. Okay, here you can get Z power minus M. Then here this is alpha M of this is alpha M of 1. Actually this is 1. Okay, no need to take actually the multiplier, so you can directly draw like this. This is alpha M of 2. This is alpha M of 3. This is alpha M of M minus 1. This is alpha M of M. Okay, now right, finished. This is nothing but y of n. Here you can get y of n. Okay, this one, or y of z, that means this one. Okay, this is the direct form structure to realize this type of mth order FIR filter. Okay, now to understand the lattice structure, first we should understand the first order filter structure, and it is also called as single stage. First order or single stage lattice filter. First order or a single stage lattice filter. That means here m is equal to 1. Am I correct? M is equal to 1. Now substitute here in this equation y of n. Here in this equation you just substitute, let it be a. So from equation a, so what is the answer here? See, x of n plus summation here k 1 to m, that means k 1 to 1 means 1. Then here what is that? Alpha m of k x of n minus k, that means here x of n plus alpha m of 1 x of n minus 1. First order filter. Okay, you know this, right? So if you have difference here, first order difference, then that is a first order filter. If you have the second order difference, that means x of n minus 2 like that, that is a second order filter, of course. It's okay. This is nothing but first order filter or single stage lattice filter. So now here consider this equation as y of n is equal to x of n plus k1 x of n minus 1. K1 is the parameter which is called as reflection coefficient. Here what is this? Alpha m of 1. Okay, right? So here just take k1 here in the place of alpha m of 1, that is called as reflection coefficient. Okay, so now coming to the structure realization. So how can you realize this one? Okay, see this. What is the equation here? So I am writing again, y of n is equal to x of n plus k1 x of n minus 1. K1 is here alpha m of 1. Am I correct? Yes, alpha m of 1. So now here, see this, how can you draw this one? Okay, lattice structure form. Okay, first I am drawing, later I will explain this one. Okay, so see this, x of n, then here add with the so here what is the output? X of n minus 1. Am I correct? Right. And then so see here, here is a x of n which is added to the x of n minus 1 into k1. Then you can get the y of n. How simple it is. See this, right? First order filter. Okay. And now here use from the same structure, use this one also to develop the further or higher order filter lattice structures. That is the benefit here, that is the advantage here. So that's why it is said to be lattice structure, like this, in this form. Okay, then so see this, this is first stage means I am using the some other variables here, f naught of n, and this is g naught of n. Okay, f naught of n, g naught of n. But the second stage, f1 of n, g1 of n, like that. Now this is said to be g naught of n minus 1. Okay, am I correct? Now here let it be, this is f1 of n. Since it is a second stage input, here I am taking f naught of n. For the second stage, f1 of n, that means first stage output y of n is nothing but the second stage input. That's why here. So now this is nothing but, what is this? If it is g naught of n, for the second stage, it is nothing but g1 of n. Okay, right. So in this way here, smartly you just develop the structure. Okay, see here, based on these two values, you can implement the what is that higher order filters. That means the structure, this structure is repeated and same structure is used to implement m stage filter. Okay, or m number of what is that realization, m number of filters. That means here is a one filter, first order filter. Next one, if you add the same first order filter, it becomes second order filter. If you add the another first order filter, it becomes the third order filter, like that. Okay, so right now from this we just find out the what is that, what is f1 of n and what is the g1 of n. Now here behind x of n, y of n is there, but we should focus on what is f naught and what is g naught and what is f1 and what is g1. Similarly, f2, g2 and so on, fm, gm. Since here we are using m stage filters, m order filters, that's why. So now see this here, what is the f naught of n? Simply x of n. What is the f1 of n? That is nothing but of course y of n, which gives the what is that, x of n plus k1, x of n minus 1, of course. But in terms of fg, what is that? F naught of n plus k1 g naught of n minus 1. Am I correct? Which is equal to x of n plus k1 x of n minus 1. Very simple one here. If you understand this one, you can easily draw this one. Very simple. Then g1 of n is nothing but, what is that? Observe g1 of n. What is that? F naught of n into k. Am I correct? Right. Plus then g naught of n minus 1. Am I correct? That means k into x of n plus x of n minus 1. This is nothing but g1 of n. Okay, right? You can get the desired output here at this position f1, and this one helps you develop the further stages of the filter. Okay, right? So this is nothing but, what is that? First order lattice structure. Very simple. For second order, what we will do? You just take same thing, structure here, and then connect here these two, f1 and g1, and then you can get the f2 of n and g2 of n. There f2 of n is nothing but second order filter output, that is f of n. Right? Simple. Okay. Now here, coming to the second example, what is that? Two-stage lattice filter. Two-stage lattice filter. In the similar way, just draw this here, What is two-stage lattice filter or second order filter? Second order lattice filter. How can you realize this one? See this, first, what is y of n here? First one is x of n plus, next one is alpha m of 1, x of n minus 1. Here, of course, m is equal to 2. Am I correct? Here also, m is equal to 1. So now here, here you should write here. What is that here? Alpha 1 of 1. Okay, here alpha 1 of 1. Very good. Okay, right? Here also. Okay. Alpha 1. Okay, right. So now see. Okay. Now here also m is 2 means alpha 1. Okay. Plus alpha m2 means alpha 2 of, here see formula, right? So okay, here k 1 to 2. So first here m is 2 always, so alpha 2 of first one 1, next x of n minus 1, then if you apply k2, alpha 2 of 2 into x of n minus 2. So see here alpha 2 of 1, here also alpha 2, right? In the first order you have the alpha 1 of 1, but in the second order alpha 2 of 1, alpha 2 of 2, in the third order alpha 3 of 1, alpha 3 of 2, alpha 3 of 3, in the mth order alpha m of 1 and alpha m of 2, and so on, alpha m of m, like that. It's okay, right? Now x of n minus 2. Okay. Now here see how can I realize this one with respect to lattice structure. Very simple. First see first write adders, and then delay, then adders. Now here is the first stage output. Here just this has the coefficient. Okay, now, and then here let it be, this one is nothing but k1 and this is nothing but k2, reflection coefficients. So here this is x of n. Now here this is f naught of n and this is g naught of n, and here is k1, k1. Now here you can get f1 of n, here is g1 of n. Now same thing, right? Again draw this adder, delay this unit, now adder, now use this. Here also take the multipliers k2, k2. Now here this is f2 of n and this is G2 of n. Here is Z inverse. Okay, right? So now here this F2 of n is nothing but Y of n. Okay, now this is nothing but two-stage lattice filter structure. Two-stage lattice filter structure. Okay, now here what is the output here? What is the output? So see this. What is F1 of n and what is G1 of n? First write like this. And then similarly write F2 of n, G2 of n. Okay, what is F1 of n? Here, tell me. X of n plus K1 x of n minus 1. What is G1 of n? K1 x of n plus x of n minus 1. Am I correct? Or that means here this is also equal to. So I am writing in another form. So see this. F0 of n plus K1 G0 of n. Here K1 F0 of n plus G0 of n. Am I correct? Now what is F2 of n? From F1. That means F1 of n plus K2 G2 of n. K2 G1 of n. K2 F1 of n. K2, what is this? G2 of n. K2 F1 of n plus G1 of n minus 1. Am I correct? Here? Here also. What is that? G0 n minus 1. K1 here also G0 n minus 1. Am I correct? Right. Okay. K1 G0 of n minus 1. Okay, here also K2 G1 of n minus 1. K2 G1 of n minus 1. Okay, right. Then here from this, here just substitute F1 of n, this one, then G1 of n minus 1. So you know the G1 of n and then write here G1 of n minus 1. Then you can get the F2 of n is nothing but what is that? Y of n. Y of n. Okay, right? That means F2 of n is nothing but F1 of n means x1 of n plus K1 x1 of n minus 1 plus K2 G1 of n minus 1 is nothing but K1 x of n minus 1 plus x of n minus 2. That means substitute n is equal to n minus 1 there, and then you can get this one. X1 of n plus K1 plus K2 K1, common this one, x1 of x of n minus 1. So there is no x1 here, x. Right? Then plus here K2 x of n minus 2. K2 x of n minus 2. Now here f2 of n is equal to, what is that? X of n plus, if you common k1, 1 plus k2 x of n minus 1 plus k2 x of n minus 2. Okay, right? So that means here this is nothing but here alpha 1, alpha 2 of 1, and this is nothing but alpha 1 of alpha 2 of 2. Am I correct? So x of n plus x of n minus 1 plus x of n minus 2. So here written like this, but it is not, it is wrong actually. So here don't consider this one. Okay, right? So don't consider that one. Just first of all, based on the repetition of the first structure, develop this one. Now at last here we just assign the coefficients. That means here alpha 2 of 1 is nothing but k1 1 plus k2. Alpha 2 of 2 is k2. Now what is the k1 here? Alpha 2 of 1 divided by 1 plus k2 means alpha 2 of 2. In this way we just find out the deflection coefficients. Okay, right? The first one depends on alpha 2 of 1 by 1 plus alpha 2 of 2. K2 is alpha 2 of 2. If order increases, you just find values like this. Okay, right? So here this is nothing but these two are here, k1, k2 are called as reflection coefficients. Reflection coefficients. Okay, right? So in this way just draw the here m stage lattice filter, m order or m stage lattice filter. Here just here note down here what is that simple thing: first stage, second stage, third stage, like this. Now here finally last stage. Okay, right, like this you just implement. So here is x of n, first stage, here second stage, third stage, at last how many stages for m order? m minus 1, m minus 1st stage. Okay, so okay, here f naught of n, g naught of n, here f1 of n, g1 of n, here f2 of n, here g2 of n, and here is fm minus 2 of n, gm minus 2 of n, here f m minus 1, capital M minus 1, that means a small m. Okay, small m of n. Here is g capital M minus 1 of n. It is nothing but y of n, that is fm of n. Okay, now here that means you just draw all the structures like this. Okay, that means m minus 1 stage means m minus 1 stage lattice filter means What is that? See this. So just add a, here also add a cross multipliers and then add, and then here use Z inverse. Same thing, same structure. Here what is that? K M, small m. Don't confuse with small m and capital M. Here M up to small capital M minus 1. Okay, M stage means capital M minus 1. Okay, now here you can get the output. So here input is Fm minus 1 of n. Here Gm minus 1 of n. Like this. That's it. Okay, this is nothing but Gm of n. Here Fm of n. That's it. Okay, so in this way you can develop the M stage lattice filters. Okay, now here you can write the Fm of Z also. What is that? Hm of Z into X of Z. Here Hm of Z is Am of Z into X of Z. Now what is the Am of Z here? Fm of Z by X of Z. Right? So here X of Z is nothing but F0 of Z. Am I correct? First one, initial one. F0 of Z. Okay, in this way we can find out the system transfer function also. Okay, right? Thank you.